Cześć, jestem Steve. Inni umiem mówić po polsku. I hope that is Polish and correct. Hi, my name's Steve. I'm going to talk to you today about Docker for .NET developers. It touches on .NET. We don't go too deep there, so even if you're not a .NET developer, I think there's some intro material here. I'm a Microsoft MVP, and I'm a senior software developer for a company called Madgex. We're based down in the south coast of the UK in a town called Brighton. We do primarily recruitment software as a service products, so we're best known for our job board platform, which we sell to customers like The Guardian, Washington Post, who use us to run their online digital job boards. The topic I'm going to cover is quite vast. I'm going to try and pack a lot in. If you miss anything and you want to get in touch afterwards, do reach out to me on Twitter, and you can find some of the material that I'm covering on my blog as well. What we're going to cover is mostly we're going to look at the journey that we took at Madgex to Docker. So why did we start using it? What problems were we looking to solve? And along the way, I'm going to talk about what it is, how we can use things like Docker files, Docker Compose, and we'll sort of move towards the end at looking actually how we can do builds and production deployments using Docker as well. So I want to start with what is Docker. I think most people have heard the term Docker, even if they're not using it. Out of interest, is there anyone in here who hasn't heard of the term Docker before? OK, good. So it's pretty much won out as the containerization technology that's kind of winning out in the industry at the moment. And containers ultimately offer us a really nice, frictionless way to do development and deployment. There's a few key terms I want to just touch on before we begin. So there's this concept of an image, which is really just a template for a container that we're going to run later on. So we build our images in advance. Those are a package that contain all of our dependencies that we're going to need. And then when we're ready to run that, we can put that on any host and start containers from that image. And we can run multiple containers from the same image on the same host. We can run different containers. They run in isolation from one another, so they don't interfere with each other. And they have limited access. They're kind of sandboxed in a way. And then the host is just that physical or virtual machine that we're going to run our Docker containers on. A common question that comes up, common comparison that gets made is why would you want to use containers over something like virtual machines, which is a technology I think people are far more familiar with. And it comes down to a number of kind of small but increasingly useful benefits. So I want to start and just look at a virtual machine stack here. So this is a kind of traditional stack. We've got a physical host. We're running a host operating system. And then we've got the hypervisor layer that's going to abstract or virtualize the hardware on that machine so that we can share it among all the virtual machines that we want to run. In those virtual machines, we're going to install a full guest operating system. And on top of that, we can layer any dependencies we have to run our application code. So that might be things like the .NET framework that you want to install in there. You might need to install and configure IIS if you're running websites on a web server. One of the things with virtual machines is we can have one application in there, but we can also have many. And it's quite common to have a web server running multiple websites, for example. With Docker, the picture looks a bit like this. So we've still got that physical host. We've still got the host operating system sitting on top of that. And then we have the Docker engine, and this is the software layer that's going to let us, rather than abstracting the hardware, abstract away the kernel. So we can now share and virtualize that kernel across all of the containers that we're going to run. And that's kind of the big difference, because now we're taking advantage of that sharing to reduce the size of the things that we're actually running. So inside the containers, all we really need is the file system that we want to run on top of that kernel. So for example, we might have an Ubuntu host machine, and we might want to run Debian or maybe Alpine containers on there. We just layer in that small veneer of a file system on top of that shared kernel. We then still need to put in the dependencies we have for our application, and then we can have our application code itself. With containers, we tend to come to a one-to-one relationship. So we will run one application, one process inside the container. So slight different shift there, and again, this is just around how we're going to actually deploy these things later on. There's some benefits of doing this approach. So one of the key ones is this small unit of deployment. With a Docker image, your file size is typically a few hundred megabytes, maybe even under 100 megabytes for the full image. That includes the OS file system layer, your dependencies and your application code. It obviously depends on what you're running in there, but your starting point is very small. So that makes these a really good candidate for deploying to different environments. We can ship these up into the cloud very easily. We can put them onto different environments. We haven't got to push around maybe gigabytes of virtual machine hard disks, for example. When we're running them, they're also very lightweight at runtime because we aren't booting a full operating system. With virtual machines, you tend to allocate enough memory and CPU to run that OS. But now with containers, the OS is already running. We're running the kernel on that host. So all you need is the memory and CPU for your application. So typically, this means we're going to pack many more containers onto a single host machine. And we can get much better advantage of costs, for example. We're going to just make better use of that overall host machine. Another benefit is the startup time. Docker images typically start in under a second or so. Obviously, you need to bootstrap your app in there as well. But the containers will open up very quickly. And this is brilliant for scaling scenarios. If you want to scale in response to things like a sudden peak of requests coming into your application, or maybe you've got a process that monitors a queue and there's a spike in the messages, you can scale pretty reactively to that because your containers can start up almost instantaneously. With virtual machines, you tend to find yourself over-provisioning or trying to sort of preempt when you might get peaks of load. And so that can tend to mean that you're spending more running additional VMs that you may not actually need. And then finally, you get reliability from Docker images, because Docker images are immutable. So you define in a file what you want to install into that image, and you build it. And once you've built that image, no one can go in and change it. And one of the key benefits is then you can deploy that to any environment, and you know it's going to run in the same way as it did in your development environment or wherever else you've chosen to run that image. With virtual machines, it's not uncommon for someone to go in and patch a production system or maybe install additional dependencies in there that tend to break your app. And it's also possible to get this drift between maybe staging environments and production environments because they have slightly different versions of things installed. With Docker, those images don't change, so you know you can just deploy those to those different environments. I'm going to talk briefly about Madgex Insights. So this is the product we started building a year and a half, 2 years ago at Madgex that's kind of taken us on this journey to Docker. Madgex Insights is a reporting and analytics tool that we've built for our customers so that they can get better insight into the data that their job boards are producing. So there's many sort of millions of events that we're streaming out of these job boards, job views, job applications, and what people are searching for, that they can use to get better insight into what type of things they need to be selling, what type of recruiters they need to be approaching. We made a few key decisions when we started planning this system. We knew we were going to be dealing with a lot of volume, and so we decided that it made sense for us to go for a microservices approach. We have lots of different pieces involved in this, things to collect data, things to process that data and aggregate it in various ways or enrich it with additional information. And so each of those is really a single responsibility, and microservices is a great use case for that. That also gave us the possibility of discretely scaling these things. So we can scale each of these services in response to the actual load that they're getting, and we can also independently version them, independently release them. We also decided we'd use .NET Core and ASP.NET Core, which was a slightly brave decision. We were in the sort of release candidate phase, I think, and things did change a bit, things broke. But one of the key things we were looking for was cross-platform support. So we wanted to be able to potentially host on Linux. We didn't at the time know we were going to go Docker, but Linux was a cheaper hosting option that we were considering. And then there's some other advantages from things like .NET Core and ASP.NET Core in terms of performance that we also wanted to get advantages from. And then the final decision we made was that we were going to create the front end for the application in a Vue.js application, or more to the point, our front end team were going to build that. And I'm on the back end team, so we were building out APIs that were going to drive the data that they needed. And looking in at that architecture, this is kind of just looking at the front end component, really. And at the front there, we've got the Vue.js application, so it's a single-page app, and it's going to make API calls. We decided to break our sort of front-end APIs into these three parts, the report, the user, and the schedule API, because each of those is its own domain, really. They don't need to know about one another, and this, again, gives us the possibility to scale those things differently. The report API, for example, typically gets the most load, and it also means that we can independently release those things. And as long as we don't change any API contracts that we've got with the front-end application, we can release those many times a day. Each of those has its own Postgres database, so they're sort of entirely separate databases. And then the report API talks to a backend API that we call the query API. So report API deals in kind of user-facing language. We deal with things that we call report definitions. So the metrics, dimensions that people want to see on their report, any filtering and sorting that they want to do to the data. And that's sort of what the report API deals in. And then it calls down to the query API, which can take those definitions, translate them into one or more Elasticsearch queries to go and get the data out of our data store. We decided to break that query API off because we can then share that logic or share calls through that API from other supporting services that we have as well. One of the things that we realized as we were kind of sketching this out, though, was we had a new challenge that we hadn't faced before in terms of microservices means that the front-end team would have to spin up these APIs in order to work with them. That, or we would have to host versions for them, and then we run into problems of whether they're treading on each other's toes, trying to work with the same copy of an API, and how would they work offline with this? If they wanted to take this away and work outside of the office, could we give them a way to do that? And that's kind of what led us towards looking at Docker. We were kind of researching solutions. Docker was obviously starting to gain quite a bit of traction a couple of years ago, and it looked like it might offer some of the advantages we needed to solve some of these problems. And so with that in mind, just put that to one side for a second, another challenge we wanted to try and address was our existing developer workflow, which looks a bit like this. So our existing full framework, 15-year-old sort of product that we've developed over a long time, big enterprise piece of software, takes a while to build. And if our front-end team need to work on that, the current process has been that they need to pull down the main platform solution, which is many tens of projects. They then need to pull down client-specific projects that contain all of the client-specific customizations and UI work. And then they need to build both of those. But this is full framework, so it needs to be built on Windows. And so our front-end developers who are traditionally Mac users end up having a Windows VM installed on their Mac. Then they have Visual Studio installed into there. Then they have this huge checklist of all of the things that need to be set up correctly to run this. So they need to have RIS set up in a certain way. They need certain registry settings. So there's this checklist and script that they go through. And then they're in a position where they can actually build the software. That takes a minute or two. Then they can run it and actually start work. And so this feedback loop that they've got is not particularly efficient. We're looking at a few minutes to get up and running, and if someone asks them to change clients and start doing something else, they have to pull down a different client and rebuild everything. So we wanted to try and get away from that kind of workflow as well, and also solve this problem of running up multiple things. And so where we're at today is this kind of picture. Now this has been a journey. There's some steps between this that I've kind of not shown through time, but we've kind of iterated on the approach to moving to where we are today, which is basically this flow. So now what we do as part of our CI system is every time we commit anything on our backend APIs, that gets built as a Docker image. And then what we do is ship that Docker image up into Amazon's container registry, which is an online registry for Docker images. And if you've not heard the term registry, just think of it a bit like NuGet. So it's a store for Docker images. You can run them privately in the cloud. You can have shared registries if you want to. And you can also run this locally on-prem if you need to. So it's just somewhere to push images to that other people who have access can pull them down from. So with those then built and pushed into the cloud, all we do is give our front-end developers a single file called a Docker Compose file. And we'll look at what that looks like in a minute. But that Docker Compose file just defines a set of containers that we want to run together at the same time. So in this case, it's the set of APIs that they need to spin up. So we give them that file. They run one command called Docker Compose pull, which will pull any latest images down. And then they use a Docker Compose up command, which just starts all of those services on their machine. And we even include a Postgres database inside a container for development, so that they can kind of spin up with a known database state. And if they really need to, we can actually spin up Elasticsearch inside the container as well. So at this point, the flow is much less time. We're talking sort of maybe 10 to 30 seconds to run those two commands and get spun up with these services and start working. And if we change stuff, it's very easy for them to grab the latest images again. So that was kind of where we've moved to. And the team were quite happy. They said, this is amazing. because this was a kind of a culture shift, a kind of workflow shift for all of us as we started working out how this was going to work and how the teams would interact. But we quickly realized it meant that as back-end developers, we could move very fast, and the front-end team can just catch up with those images when they're ready and start working against them. And both teams were working very, very rapidly to iterate on the design. So, first demo, I'm going to just show you how we can take an existing application and make it run inside a container. So I've got a solution here. Not sure if we can see that. And basically, this is a standard web API solution from ASP.NET Core. So if you go in and just use the API template that's there, you'll get this API project without this Docker folder at the top. So we've just got a very simple values controller in there that is just returning 2-string values, nothing exciting. And we want to run this inside a container. One of my options today, and we didn't have this when we started, is we could go in and choose Add and Docker support. So if you're running the latest version of Visual Studio, this is a great way to get going. It will add a Docker file for you. It will add things like Docker Compose files and some scripts. And it will actually integrate nicely with Visual Studio. So when you start debugging, it will actually spin up a container running that code, and you'll be debugging live into the container. So that's a really great way to actually test it in the real environment it's going to be running in. We didn't have that, and I still think this is worth showing because this just shows how simple it is to do it manually. So all I added was a text file called a Docker file to the project root, and in that file I have a set of commands. And those 5 commands are what define how we're going to build a Docker image. So the first command there is the from command, and the from command specifies a base image. So with Docker, you've got this layered architecture approach that you've got each image is immutable, so you can't change what's in the image, but you can build a new image based on an existing one and just layer in some additional things, and then that becomes your new image. So in this case, there's an image called ASP.NET Core Build that the Microsoft team maintain, and they push up onto the Docker Hub. And you can get this image, and it contains everything you need to build .NET Core applications. Do not screenshot this or photo this and take that away and think that's great, run it in production. It's not really production ready. It's great for development. It's OK for prototyping. But we'll see a more realistic Docker file towards the end. After the name there, so we've got ASP.NET Core is kind of the name of this image, and then we've got colon 2.0, and that's the tag, the version of this image. So Docker naming gives you this tagging approach so that you can have different versions of the same image as new versions of that particular thing become available. So in this case, I'm saying explicitly I want the 2.0 SDK. I want everything that's going to support the 2.0 pieces. If I was running a 1.1, I'd ask for the 1.1 here. The next command is our working directory. This is just saying I'm building this image. This is where I want to be working inside that image. So which directory am I touching at the moment? And then we need to get source code from this machine. So in this particular example, we're actually going to use this image to build our source code for us as well. So I'm going to copy the source, and the first argument here is the source of that, and it's relative to where we're building this image. So whenever we run the Docker command, we can pass it the path to a build context, and that just says this is the directory that contains all the files I want to put into this container potentially. At that point, I've said, actually, I just want the source folder and this docker.net devs demo 1. That was a really bad name for a demo project. And then the next part here is where I want to copy that to into this image I'm building. In this case, the dot, if you can see it there, is just saying this is relative to the working directory. So I just want to copy everything in that docker.net devs demo 1 into my /app folder in the image. Then we can run commands, basic commands. So I'm going to run a .NET build. This is just part of the .NET command line tooling. So this is going to build our source code and create a built assembly from it. And then finally, this entry point is the pointer to Docker that when it starts a container from this image, this is what I want you to run. So typically, one container is one process. And in this case, we're saying run the .NET exe command with the run argument to run our built code. As I say, this isn't production ready, but this will get us an image going. So if I jump over to a console, I'm just in the directory where that project lives. And I could do a docker build command. I need to give this a name. So much like the ASP.NET Core build image had a name, I'm going to call this demo 1. And then this last part is where is the build context? Where are the files I want to be potentially putting in this image? And in this case, the dot just says, well, I'm in the directory, so it's relative to where I am now. If I run that, that was really quick, and it's partly a cheat. Docker, when you do builds, it caches the different steps. So if nothing has changed in the code, it will just use the cached image it already has. And this is great for sort of speeding up the build process if you're doing repetitive things and you're not changing anything in those layers. But you can see there, successfully tagged the demo 1. So if I now want to run this, I can use the docker run command. Now this is an ASP.NET Core API project. It's going to run under release, so it's going to be listening on port 80 with Kestrel. That is not automatically available to you on the host machine. If you want to access that container, you have to tell it that when you start it. So I'm saying, I want to run this, and I want to expose a port. And I'm going to expose port 80 inside the container to port 6001 on this laptop here. And then I just need to say what I want to run. So I want to run the demo 1 image that I've just built. Issue that command. It's going to spin up a container. And then inside there, Kestrel is going to be started up, and you can see the log output. And we can see Kestrel is now listening on port 80, so that's now running inside a container on this machine. And just to prove it, if I jump to here and just do localhost 6001, which is the port we exposed it on, wonderfully 2-string values. So we've just taken that existing application, we've given it one Docker file that says how we want to build an image, built the image, and then we started a container running from that image on our machine. I'll briefly go into this kind of concept of layering. I don't have time to kind of go into the full details, but this layering thing is not just one layer. You're not just calling that ASP.NET Core build image and getting one image underneath you. There's multiple layers, so that in itself will be calling and creating an image based off of a previous image that has even less stuff in it. So if we work from the bottom up, the first image in any Docker sort of image stack is the scratch image. This is something Docker provide that just gives you a base. There's nothing in it. The next layer is that file system layer. So we're sharing the OS kernel on the machine, but we need to layer in some kind of OS file system so that we've got the basic functionality that the OS provides on top of that kernel. So in this case, the ASP.NET Core images as of 2.0 are based on Debian Stretch. So we add that in. Then there's a couple of layers that add in some additional build type dependencies, things like curl, wget, git, mercurial. Those get added in these layers. Again, this is part of the reason why this wouldn't be something you'd want to run in production. You don't generally need those tools inside an image for production of an ASP.NET Core runtime. But during the build, these might be useful. Then there's the .NET Core SDK layer itself. This one now brings us up to about a total size of 580 megs. So when I said earlier these images are quite small, they are, but only if you only include the bits you really need at runtime. So again, this is why this isn't production ready, but it gives you all of the tooling you need to actually build your source code inside that image. And then finally, there's the ASP.NET Core image. So that's the ASP.NET Core build image that we were using with our from command. So as a result, we got this entire stack below our application, and then we layered our application code in top. Now, I said one of our problems was running multiple things at the same time, and that Docker sort of file gave us a way of building one image and running one image. That wasn't what we wanted to have to give the team. We didn't want to make them have to run each different thing individually. So we can use Docker Compose. So I've got a second solution here, very similar to the first, except now I have two projects, two API projects. The first is the back-end service, and that's going to provide some raw data. So that's the equivalent of our query API in our real-world example. And then the front end is the one that the front-end single-page application will actually end up calling. The back end looks almost identical to what we had before. So we've got a values controller returning a couple of values, string values there. The controller on the front-end API, a little bit more in there. It doesn't really matter the detail. But ultimately, what we're doing is we're using the HTTP client to make a call to that back-end service. We're going to get the URL here and build up the URL that we want to call. And this is just coming from ASP.NET Core configuration. If you haven't seen that, take a look at ASP.NET Core documentation. But it's a really nice configuration system that allows you to kind of start with configuration that comes out of, say, JSON files, but ultimately could be overridden later on by environment variables. So we're going to get that value from there, and then we can make our HTTP core. So in this case, I'm not doing anything with it. I'm just going to spit it back out again. The Docker file for each of those Looks the same as what we had before, pretty much. And the piece that we're actually going to make use of then is the Docker Compose. So the Docker Compose is the thing that's allowing us to define multiple services that we want to start at the same time. So in this case, I'm defining the two services, the back-end service, and we can give it a build context. So this is the same as with that manual Docker build command, is where are the files that I want to use on my machine that are going to be involved in building an image for us. We can give it a container name just so that it has a friendly name when this thing gets started up. And then that's all we need to define for the back end. For the front end, again, a build context pointing at its project where its source code lives. Then I have this ports command. So this is the equivalent of the -p that we did manually with Docker run. So it's saying, I want to start this service, and I want to expose port 80 that's running inside this service out to the host machine on 5001. Then I've got my environment variable. So when you start up Docker containers, you can pass in the environment variables. And this is how I'm overriding the configuration in ASP.NET Core. Now, one of the really nice things is we didn't need to expose any ports on the back-end service because we never expect to talk to that directly through the host, through this device. I only expect to call it from the front-end service. And because these two are started up together in Docker Compose, they get put into a Docker network together, and they have access to a basic DNS in there so that they can actually talk to one another. And so that's kind of like an isolated network that they're allowed to work on. So in this case, I can just pass in this friendly name, which is the name of the service, to say I want to call call the backend service from the front end. Again, I give it a container name, and then I can use this depends on to just kind of give Docker Compose a bit of a hint about what order these things should be started in, because the front end's not going to do much if the back end hasn't started up. And so that's all I need to define. And then if I jump over to the console again, I'm just in the root where that Docker Compose file lives. And if I do a Docker Compose up, which is pretty much the only command we need to give our front-end team, it will spin up each of those services. We should see the output from both of those containers in a second as it trundles through. So we can actually see the front end there is now listening on port 80. So that's the one we exposed through on 5001. So if I jump back over here and go to 5001, I'm getting the values there from my front-end container, but the values are coming from its call to the back-end container. So now we've got two services that are dependent on one another running on my machine in containers, and all we had to do is just create that Docker Compose file and give it to our front-end team. So we kind of got quite excited about Docker at this stage. We were solving a lot of development time problems, and we started wondering, well, actually, can we take this a step further and start running with Docker in production? Because we needed to solve similar problems. We needed to run multiple things now. We had multiple microservices. And so we were looking at ways to do that. And this is kind of the flow we've got. I'll take you through it a bit more in the next slide and demo. But ultimately, what we do now is for every service, we have a Git repository. We can commit code, push it to Bitbucket, and then we have a Jenkins server that's just monitoring those repositories. If anything changes, it will trigger its build script. And in this case, we're not building source code, which might be the kind of traditional expectation from a build server. We're using it to build Docker images. So we're just running Docker commands, building the image, pushing it to ECR, which is Amazon's container registry. And then we're notifying a service called ECS, Elastic Container Services on Amazon, to say, there's a new image here, we want you to put this in production, please. And we'll look at ECS in the next slide or so. So at this point, we've got these things running in production. And this is actually a continuous deployment process now. We don't have any gates on this. If we push code, it's going live in about 5 minutes. And so we have to be reasonably sure we've got tests around that. But really what it means is we can move very quickly. We can fix bugs very quickly. And we can just kind of develop at the pace that we really want to be doing. So to run in production, the other problem that kind of comes up is orchestration, because you don't really want to be manually running Docker Compose up commands and just hoping everything's fine. You also don't want to be manually kind of restarting things if they fail. So orchestration is a kind of a tool that would hold that problem for us and deal with a number of things. So it manages things like scaling, doing deployments and even rollbacks, health monitoring the services that it knows about. So if those fall over, it can restart them and recover. We need to do service discovery because typically we're running on hosts anywhere, somewhere in the cloud. We don't necessarily know where these containers are going to be started, and then we need to load balance across them. So we looked at the options, and this was a couple of years ago. There were a few around. The kind of key ones were things like Docker Swarm, Kubernetes, and there was a product called Mesosphere as well. But we kind of looked at Kubernetes and realized it was really complicated, and we didn't want any more new stuff that we had to manage ourselves. So we had a look, and we were running on Amazon anyway for the rest of our services, and we found that they had this Elastic Container Services product. And it's just a managed orchestration tool. So you don't manage your orchestration hosts. You don't have to set up your orchestration environment. You basically just say, OK, here's some host machines I want to run containers on, and here's the definition of what I want to run. And it will go and schedule those containers for you and keep them alive. So the key components, and again, we'll kind of cover this at quite fast pace because there's a lot to ECS. But the key component is the cluster, and the cluster is just a logical grouping of EC2 instances. So these are just the VMs that you're going to run in the cloud that can be your host machines where you can run containers. You can choose any EC2 instance sizes you want. You can mix and match in this cluster. They can be across availability zones if you want to get sort of the availability requirements met. And also, they can be in an auto-scaling group. So if you need to scale these things in response to not having enough space to run containers, you can let that cluster expand underneath you. The only special thing about them is they come from a particular Amazon machine image that includes the ECS agent that you need and Docker. Then we define services. And services are the logical grouping of the things you want to run. So a bit like we had the services in the Docker Compose file, we're going to have services here. And in each of those, we have a task definition file which defines what we want to run. Now, typically, the good recommendation is if you've got one microservice, use one service. Don't try and pack too many things in. You can technically run multiple containers as part of a service, but your service is your unit of deployment and your unit of scale, essentially. So you want to keep these things running one thing so you can scale each one independently. So here I've said for service A, I want two of its tasks running, and for service B, 4 of them. So those then get scheduled essentially randomly across the EC2 instances we have as hosts. There are ways you can control that to some degree, but for now, let's just assume it's just scheduled them randomly. Now, these are web-facing, and we want to be able to call into these. So how are we going to do that? Because we don't know what ports these things have been given on the hosts. Well, that's where we link in the application load balancer from Amazon. And the ALB interfaces with ECS, and it knows when these tasks get started, what host machine they're on, and what port they've been given, and what service they belong to. And so it can add those into appropriate target groups and load balance across them. Now imagine we have a problem, task B blows up, one of our containers has died. That's kind of fine. We've still got 3 task Bs running, but the ALB might send traffic to the one that doesn't live there anymore. Well, the ALB is health checking every task it knows about, every endpoint it knows about. So it will very quickly realize that that's no longer responding and take it out of its target group. We're still serving traffic across the remaining 3 tasks. And then service B, which has got this desired count of 4, but a current count of 3, will just trigger a new task to be started, and then that just pops up wherever. Not necessarily on the same instance. Again, we don't really care where these are running. And then it tells the ALB where it is, and the ALB can add it back into its group. So with this, we've got the kind of continuous recovery cycle if any of these things fall over. So I'm going to try and demo that, which is slightly dependent on my network connection, but we'll give it a whirl. So I've got a website, and if I refresh this, yes. So this is running live. This is just the application load balancer URL, and I've got a string returned to me, which is very exciting. So let's imagine we've been given the task of changing this. So I'm going to change this text that I get back to hello Infoshare. I'm going to commit this change. Well, it doesn't really matter. It's just me, and it's a very descriptive message. So we'll commit that, and then once that's done, I'm going to sync that, in this case, to GitHub. But you can do this. We do this internally to Bitbucket, and that's going to push that up to GitHub. Great, that's done. I'm going to go over now to Jenkins, which doesn't need to be that big. This is what we're using to do our builds, and I'm just going to manually trigger a build of this for now. On our system, it automatically watches the repositories and does the work, but because I only run this for demos, I've just got it manually triggered. And there's a bunch of output. It's doing a build. While that's building, this is what Amazon ECS looks like. So in here, we've got a cluster. And in that cluster, I'm running one service. So this is what's running that one API that's returning that string value. Now, if I refresh this, if we get lucky, we'll actually see it happen. I'm going to just keep refreshing it and just check if we haven't quite finished the build. So at this point, we're doing the image build, and we're looking to push that up to AWS, to that container registry. Great, so that's finished. So in any moment, it's going to notify ECS that there's this new image available on, please deploy the latest one. We're just going to refresh it a couple of times. It's probably not going to do it there, so what I'll do, we'll have a look at the actual event for this service and see if we can catch it there. So in this line here, you can see it started a new task. So it's now started a task based on that latest image that I've just pushed. And if I refresh again, we'll probably see now it's registered it into the ALB's target group. So now it's the load balancer knows about this thing, and it can start calling its health check endpoint to see if it's actually healthy. At this point, the original task is still running, and it's still serving traffic until this one is considered healthy. I'm not sure if we're going to see it finish in time, because it seems to be a bit slow. Refresh a couple of times. Yes, OK, so now it started draining connections. The new task is healthy, and it's draining connections. And if I jump over and refresh that, I've now got my change text. So we've just done a complete deployment there with zero downtime using Docker images. Actually, what I'll do, let's have a look at the code, because that would be useful. So I've got a Docker file here. This is slightly more intimidating than the last one that I showed you. Don't worry about the details too much, but I'll just summarize what the differences are. So the first is that we're using a feature called multistage Docker files here. So Docker added this a year or so ago, I think, and it's a really nice system. They realized people were using images as a way to do builds quite often. And so typically you'd build into one image, and then you'd have another script that would build another image, and it would pull the output from the first, and it was a bit of a manual process. Multistage lets you do that all in one Docker file. So now, I'm still using the ASP.NET Core build image I did before. I'm being very explicit now about the version I want to pin it to the exact SDK version that I want for the version I'm building. And now we have this as published, so that lets me give this stage a name so we can refer to it later. Now I'm doing copy as we did before. I'm just copying in the solution and the project files here. The reason I'm only bringing those in is because we, again, can take advantage of caching. So that doesn't change that often. I don't often change the package dependencies in those CS-proj files. So this part of copying those in and then running .NET restore can actually be cached on the build server. And unless those files change, those steps aren't going to have to run every time we do a new build. So that just lets us get slightly quicker builds. Then once I've got those restored, I can actually copy in the tests project and the source project that we've got. I can do a build on those, and then I run .NET test. So a lot of people ask, when do you run unit tests, and how do you manage that as part of a Docker-based CI system? Well, we do it inside this first stage. If any of those unit tests fail, that's going to fail the Docker image build, and Jenkins build is going to fail afterwards. So presuming those pass, we then do a .NET publish. So this is all part of the .NET command line tooling. We do a .NET publish, and we just specify the output directory. This is inside this first multi-stage image here. So we're just inside an image. Now, we have another from command. And this kind of is what points out that this is a multi-stage build, because this second from command is now just using ASP.NET Core, which is actually the ASP.NET Core runtime image. So all we have is the .NET runtime and the pre-built sort of NuGet cache of our ASP.NET Core packages, so that we can actually use that to run an ASP.NET Core application. This is, for reference, about 140 megabytes compared to the 700 or so of the build image. And if you use ASP.NET Core 2.1 on their Alpine-based stuff, I think it's down to about 70 megabytes for the complete image. I've got this expose command. This is just explicitly saying I'm going to expect that port 80 is going to be exposed from this. You don't have to have it, technically, but it's good to have it there because it's essentially documentation for what this image is going to look like. I've set the entry point. This time it's the .NET XE, and I give it the actual DLL name that it's going to run, because we've only got the runtime. We haven't got .NET run commands, and we haven't got .NET build commands. There's no command line tooling included in this image. And then that's slightly out of order. Again, caching, because all of those first three steps rarely ever change. So we get those cached for us on our build server. And then finally, I'm ready to actually copy in the built code from our previous image. So I use this copy command. This time I can give it an additional argument from publish. So that's saying I want to copy from the first stage image that we named publish. I want to copy from its publish out folder where we've now got some DLLs that we built. And then finally, just copy it into my app folder. So now I've got my built DLLs inside this runtime image, but no source code, no additional unnecessary dependencies. Our build script in Jenkins looks a little like this. Ignore all the sudo commands, that's just to make it work on my machine. But we're just running Docker commands mostly. So I do a Docker build. I tag it. The name looks a little bit longer because when you want to push things into a registry, you need to prefix them with the path to that registry, or the URL. So that's that first piece. Then I've named it Docker demo-service A. And this last part is the tag. And I'm going to actually build this dynamically. So I'm actually going to use the git commit ID in this case as the tag. So every image we build, we can tie back to the exact commit that created it, or the code that went into it. You could do versioning there. You can have version numbers and write those in however you want to version your individual images. Some commands to log into ECR. And then I can do a Docker push. That just pushes that built image up to the registry. I then do some cleanup because it's a good idea. So I'm just removing this image now. I've pushed it to a registry. I don't care about it being on my build anymore. And then this command is just doing some transforms. So the task definition is the definition file of what the service is going to run. And because I'm naming this image very specifically, I'm going to need to put in the right git char on the tag for that image. So this is just going to look for anything that's %git_char and replace it with the environment variable git commit that comes from Jenkins. So we get our git commit ID in there. Then we register the task definition with Amazon Container Services, and then we update the service and call that, which just basically says start deploying out using this latest task definition, which also points to that latest image. And then once it does that, it will do the piece that we saw happening behind the scenes to roll that out. And then finally, the task definition itself, nothing too exciting about this, but that's where we define the image we want this task definition to point to. And on the end there is the %git char that's going to get replaced by that transform command. So that's going to actually point to the commit ID that this image is built based on. And then the final thing I want to highlight in here is just this port mapping. So very similar to the -p that we did when we were running this with the Docker command, or the ports command that we used in Docker Compose. We need to expose a port out. The container port is still 80. The host port here is 0, because we want to be able to run multiple instances of the same thing on the same host. If we fix a port there, we're not going to be able to do that because we'll get a conflict. So port 0 in ECS is just dynamic. I don't care what port you give me. Once it gets given a port, ECS will know where it's running, and it can tell the load balancer what port to find that instance on. So that's the kind of build process that we've developed. So as I sort of draw to a close, I just wanted to kind of cover off some of the challenges we faced along the way and some of the lessons we've learned, because hopefully if you're going to start doing this, it might save you some time. I think there is a little bit of a learning curve to Docker, but those first 2 demos I showed you where we kind of built that quite naive Docker file manually with 5 commands is all you really need to get going. So it's quite a shallow learning curve. You can build a Docker file, start a container from that image very quickly. If you want to run multiple things, Docker Compose itself is not particularly complicated. And it's only when you start doing the more advanced stuff, like thinking about building optimized file-sized images for production, that you start to have more thought going into your Docker files there, like we had in that final demo. But you don't need that from day one just to experiment and just to work in development. If you don't have anything you want to containerize yourself, Docker is still a fantastic tool for development time prototyping. So if you need to run Postgres to test something, or you want to run Elasticsearch because you want to try that out, or End Service Bus, all of those things are available as images on the Docker Hub. You just pull the image, start a container from it, and then you're running that on your machine. But you haven't installed anything, you haven't potentially introduced anything that's going to break anything else on your machine. When you're done testing, you kill the container, and you can get rid of the image if you want to. So at the moment, we're testing some things, and I'm doing this exact approach. I'm running a small cluster of Elasticsearch instances locally in my dev machine, just in testing inside containers. Amazon ECS that I showed you, a little bit complex. I think it's probably less than learning like Kubernetes fully from the start if you want to sort of manage everything yourself. There's a few key terms in there, and I think the biggest tip we've learned is to use CloudFormation templates. So our systems team that kind of deploy this have put everything into these CloudFormation templates, which in Amazon is just a definition of AWS services you want to run together and sort of link together. And so our team can very easily make changes to the environment just by adjusting those files, which live in source control, and just roll them out. And if we wanted to create a duplicate environment, for example, we can do that by just running that CloudFormation template into another part of AWS, and then we have a complete replica if we need that. But with ECS, do be aware of vendor lock. So this is a managed service. This is bespoke to AWS. Azure have their own offerings now based on Kubernetes. If you use any of those solutions, that's fine, but just be aware that you can't easily transfer to a different cloud provider. So depending on your sort of requirements there, you may need to consider actually running your own Kubernetes environment if you want to be a bit more flexible. And as long as you've got the installation or the configuration of VMs that are going to run Kubernetes kind of somehow scripted, it's very easy just to then move to a different cloud provider and use their virtual machines to spin up your Kubernetes environment. Something that we ran into was logging, and this is more of a microservice challenge than it is specifically containers, but we suddenly now have this problem that every one of these tasks that we're starting up in ECS is going to get its own log file. The way we did logging is we actually just wrote out to the console, because ASP.NET Core is just a console application under the hood. So we just wrote to the console, and then when you set up your task definition, you can automatically write the console, the standard out, into CloudWatch, which is Amazon's logging. I hate CloudWatch. It doesn't really work very well. I can't search across it in the way I want to. If I've got 60 instances of a task, how do I know which one it's in? And if I search, I can't see what happened before or afterwards. So it's not ideal, and we learned this lesson. In the new system we're starting to build out, which is based on what we've learned, really, we are now doing logging with Serilog. We're using structured logging, and we're spitting that out into Elasticsearch so we can search more easily across those. We're thinking about things like correlation IDs across our services and through messages if we need to, so that we can tie the entire flow of a particular request through our application, through all of the services. And that's kind of where we're moving towards. And then finally, placement of containers. So by default, I said that unless you tell the ECS system in your task definition any specific requirements you have for running images, it's just going to start containers wherever there's free space. It doesn't really care. If you've got a service that you know needs 150 megabytes of memory to run, there's not a lot of point it being started on a host that still only has 20 available. So if you tell ECS in your task definition what your service's baseline memory is, what its minimum requirements are, you can give it a bit of guidance, and it will then only start it on a host that has the appropriate resource available. And you can also set upper limits as well. So if your containers are using too much memory and potentially compromising other containers because they've taken over that host, you can set upper bound limits at where your container will be killed if that happens. Now, that's obviously quite an extreme situation. You want to alert on that and deal with why your containers are using that much memory, but it at least allows you to control whether you bring the whole system down or not. The other option there is auto-scaling, which can kind of help in that situation. But we had that on, and suddenly we got a call from the systems team because we were using far more VMs than we thought we were, and we were costing a lot more money. So just be aware of setting those limits. And then finally, the benefits. So I think for us, some of the biggest benefits have been the productivity of development. For us on the back-end team, with microservices and with kind of complete independence from the front-end team, we can deploy whenever we want. As long as we're not breaking the external contracts of things, we can deploy changes very often, and we can roll out changes very quickly. For the front-end side, this reduced onboarding time that we've got, where people can kind of basically just get given a Docker Compose file, and they can start working with no build scripts, no checklists of things that they have to install on their machine. That's proved very useful. And we've got rid of this "it runs on my machine" arguments. We don't have problems where we're going to run this and someone will say, well, that doesn't work on mine. And you go, well, it's fine on mine. Because we're giving them images that we know work, and those work consistently. So because of that, we've got these dependable deployments. We've got this fast build and deploy process with zero downtime, continuous delivery almost for free with ECS. And ultimately, we've lowered our costs. We're running this at times, this entire system, which is dealing with 17 million messages a day, is running on sometimes just 2 VMs. Because at quiet periods, we don't have many containers running because we don't pre-provision, we don't over-provision those containers. And then on the virtual machine side, the hosts are in that auto-scaling group. So when there's not many containers to run, they just scale right down. And then at peak times, when we do have a lot of messages to process, our container volumes ramp up, and the hosts that they're running on ramp up underneath them. So With that, thank you very much. I really hope that's been useful. I don't think we've got much time for questions, but come and find me at the front afterwards, or I'll hang around outside. And if you want to reach out on Twitter or through my blog, that'll be fine too. Thank you very much.